Okay, welcome back to Real Analysis. We're going to finish up our work in section 4.5 and specific skipping to the section 4.55, talking about something that we'll call compact subsets of the real line. So just to kind of remind you and set the stage for this kind of brief conversation we're going to have in this subsection, what we were talking about last time was a condition on a set E that would be sufficient to guarantee that a function that was locally bounded on E was actually globally bounded on E. And we saw that that condition was actually that the set E be closed and bounded. There was an equivalent condition to it. Theorem 4.21 said that being closed and bounded is equivalent to every sequence having a subsequence that converges to a point in E. All right. So our main definition is going to kind of take advantage of those equivalences. We're going to define for a subset E of the real numbers, we're going to call it compact if it has either one of those two equivalent properties. It's compact if it's closed and bounded, or if you prefer, if it has that Bolzano-Weierstrass property, if every sequence in the set has a subsequence that converges to a point in that set. This notion of compactness, if you've read the entirety of section 4.5, it's actually equivalent to a couple of other conditions. One of them involves a notion called an open cover, and we may have time in this course to kind of circle back and speak about this, but I'm kind of taking a minimal approach to compactness by just using this closed and bounded or this Bolzano-Weierstrass property. The Bolzano-Weierstrass property is often a very effective way of showing a set is compact. We don't have a ton of experience with this right now, but I think the material in the previous section kind of gave the spirit of it. Compactness is often the property that's necessary when you want to show that some phenomenon that's happening locally, that is happening in neighborhoods of arbitrary points, actually happens globally. So in the previous section, that phenomenon was a function being bounded, right? So on a compact set in our new language, a locally bounded function is bounded. It's often the case that some local phenomenon will pass to the global phenomenon on a compact set, compact domain. All right. So if we kind of state that in this theorem, what we proved last time is actually that if you have a function on a compact set, then if it's locally bounded, then it's bounded. So that's kind of part of this theorem. If you take some compact set E, then you take a function on E that's locally bounded, then it actually has to be globally bounded. We proved that last time. That's the beginning of my proof here. I'll just say it right now. If E is compact, well, then in particular, it's closed and bounded. In particular, it has the Bolzano-Weierstrass property, which I'm just denoting by BWP here. So that's by definition. That's what compact is meaning for us here, locally, or at least temporarily. So we proved last time that every locally bounded function is bounded, right? That was the main theorem of the previous lecture. So the point of stating this theorem here in this short lecture is just to kind of say that, well, the converse of that is actually true, right? So it's another equivalent condition. It's another definition you could use for compactness. If you have some set E, and it's true that every function on E that's locally bounded is actually bounded, then the set E has to be compact. So I'm going to scroll backwards here a little bit if you want to. I'm not going to write it out here, but you could add a third property to this. If you wanted a third equivalent condition, um, that you could replace it with this locally bounded implies bounded condition if you want to. Right. Again, if you look in the statement of this definition 4.34 in your text, there's also a third condition there that I've kind of just cropped out, and it involves this notion of open cover, which again, we'll circle back in our course if we have time. But I want to make sure that we leave enough time to develop the calculus topics of continuity, derivative, and integral in this course. So I don't want to get too bogged down in these compactness arguments. Anything that we need to prove about compactness or compact sets, the Bolzano-Weierstrass property is certainly going to suffice. It's a nice property because it involves sequences. We spent a lot of time in chapter 2 developing material about sequences. We're used to working with sequences, so it's kind of going to be our preferred method. Preferred in the sense that it's my preferred method, and I'm imposing my will on you. Okay, so let's see if we can't prove this converse. Sorry, I'm scrolling all over the place here. What am I going to prove? I'm going to assume that I've got a function, or I'm going to assume rather that E has the property that every function that's locally bounded is in fact bounded, and I'm going to try to show you that E is compact. And to show you that E is compact, I'm going to try to show you that it's both closed and bounded. Okay, so we're going to kind of argue by a contradiction in both parts of this. So let's suppose that we've got this set E, and that every locally bounded function on E is actually bounded on E. So that's our supposition. And then I'd like to try to convince you that E is a bounded set. So suppose it's not. Suppose E is not a bounded set. All right, well then look at this very specific function. Take the function on E that's just defined by f of x is equal to x, the identity function. That's certainly a locally bounded function. I'm going to leave the details to you, but it's not bounded because E isn't. Again, this function has the property that its outputs are its inputs. Well, if the inputs aren't bounded, then neither are the outputs. So that's a contradiction. Here I've got, I was supposing that every locally bounded function is bounded, but if E is not bounded, I can make a function that's locally bounded but not bounded. That's a contradiction. So what's the only way out? The set E must be bounded. It has to be a bounded set. Cool. All right, you should kind of compare that to the first example. It was actually the second example in the previous lecture, where we looked at basically the same thing. For an unbounded set E, it was the set from 0 to infinity. So you can see that this sort of notion of being an unbounded set, it's always going to provide an example of a locally bounded function that's not bounded. All right, so proceeding along the same lines, I want to show that E is closed. So let's suppose it's not. Suppose E is not closed. So what does it mean to be not closed? It must mean that you have some accumulation point, I'm going to call it x naught of the set E, but that's not in E, right? Because if you're not closed, you can't contain all your accumulation points. The set of accumulation points can't be empty. If that was the case, you'd be closed. So there has to be some accumulation point that's not in the set. Let's call it x naught. All right. And then I'm not going to run through the details again, but by choosing, say, epsilon to be 1 over n for every n, the kind of familiar construction, we can find a sequence in E that converges to that accumulation point. It's an important construction to digest. If you take an accumulation point of a set, you can construct a sequence of that in that set that converges to that accumulation point, right? This sequence is not eventually constant because I'm assuming x is not in E. Nice. So no one of the sequence terms can be equal to x naught. Okay, good. Now I'm going to define a function. Again, you should probably stop the video and rewatch the very first example of the previous video, where we were introducing this notion of local boundedness, because I'm just kind of mimicking it here. I'm going to define a function on E by saying that for every t in E, didn't write that here, let me just kind of tack it on. F of t is just the reciprocal of the absolute value of t minus x naught. All right. Why is that well defined? Well, as we said, t cannot equal x naught because it's an element of E, and x naught is not an element of E. So that's a well-defined function. I'm not dividing by 0. I can take the non-zero number t minus x naught's absolute value and look at its reciprocal. Okay. So first of all, I claim that function's not bounded globally on E. So how to prove that? Well, if you give me some positive number m, then if I let epsilon be its reciprocal, that's also positive. Yeah. My sequence x minus x, sorry, my sequence xn converges to x naught. So I can go out far enough in the sequence. I'm just going to go out to the threshold value. There's some capital N that sequence term differs from x naught by less than epsilon. I can find such an n given this epsilon. And if I look at f of that point, at x sub n, well, then by the definition of f, it's the reciprocal of the absolute value of xn minus x naught, which would then be bigger than 1 over epsilon, which is equal to m, right? So what have I done? For any m, if I kind of highlight it, for any m, I have found a point x sub n in E, and f of x sub n is bigger than m. So m is not an upper bound, but m was arbitrary, so the function f is not bounded. It's not bounded on E. Okay, I claim this function is locally bounded. It's locally bounded, and I'm going to try to argue that with you guys right now. I'm going to give kind of one of two possible cases. So let's pick an x in E, right? And I'm going to assume that it's bigger than x naught. If there is no such x, then every x would be less than x naught, and I'm going to leave that case to you, right? It might be both. There could be both possibilities, but I'm just going to try to establish the spirit of this and then let you kind of make the appropriate changes if x is less than x naught. Okay, I'm taking some x in E, I'm assuming it's bigger than x naught, and I let epsilon sub x be half the distance between x and x naught. I've drawn the picture down here. Here's my x naught. It's not in E. Remember, it's not in E, but I pick my x. It's in E. It's greater than x naught, and I let epsilon sub x be half the distance. So the epsilon sub x neighborhood of x would look like that, right? You can work out what the endpoints of it are directly. I'm going to let you do the arithmetic, but if you take a number in that epsilon neighborhood, this number x minus epsilon sub x would be x plus x naught over 2. Stop the video and check it. X plus epsilon sub x is 3x minus x naught over 2. Stop the video and do the calculation. Okay, those are the endpoints of that interval. That neighborhood, that epsilon sub x neighborhood. So subtract x naught from everything. You get those inequalities. In my case, I'm assuming that x is bigger than x naught. So this left-hand endpoint is positive. So y minus x naught is positive. Okay. And then I look at f of y. F of y by definition is 1 over the absolute value of y minus x naught, but I can ditch those absolute values because y is bigger than x naught, y minus x naught is positive. And by this inequality, that reciprocal 1 over y minus x naught is less than 2 over x minus x naught. So I take that to be my m sub x. That's a number that depends on x. And for every y in this epsilon neighborhood of x, the output of that function is less than that. All right. So that's the definition of f being locally bounded. X was arbitrary. Well, it was arbitrary and bigger than or equal to x naught, strictly bigger than x naught. You have to try the other case, but you can just sort of modify this proof. All right. So where did all this come from? I was assuming that the set wasn't closed and I was able to construct a function that's locally bounded but not bounded. But we were assuming that every locally bounded function is bounded, so it must follow then that E is closed. And that completes the proof of the theorem. Okay, so this one was a little bit shorter. Thanks for listening.